Good morning, chemistry students. If you missed the Zoom session last Friday, we began talking about something called VSEPR, that stands for valence shell electron pair repulsion. And let me put another little hyphen between electron pair. The whole idea is that we're going to be able to predict the shapes of molecules by applying a very simple model. And that is the idea that electrons repel each other. Electrons are negatively charged particles. And around the central atom of a molecule, you're going to find a lot of electron pairs, lone pairs or bonding pairs. And those electron pairs repel each other. And because of that, the shapes of how the atoms are connected to one another are going to result in very predictable geometric patterns. And so part of the activity on Friday was to get some balloons, if you had them, and to tie them together. When you tie two balloons together, you get sort of a linear arrangement. When you tie three balloons together, it looks kind of triangular. And when you get four balloons tied together, it's a lot harder to draw, but it's three-dimensional. You got basically a balloon coming towards us, another balloon back behind the structure away from us, and then two more here in the plane of the board. And these have particular shape names. And it's going to give rise to what we call parent geometries. And so there's three parent geometries: linear, when we have two electron regions around the central atom. There is trigonal planar. That's a triangle in a plane. That means it's a flat triangle, and angles of 120 degrees all the way around. And then when there's four regions of electron density, something called tetrahedral. Okay, that's an adjective for a tetrahedron, a four-sided figure in three dimensions in geometry. So we have these three parent geometries. And we covered this basically last Friday. So if you missed last Friday, please go ahead and write this down. And everybody, pause the video and add in these two extra columns. We're going to talk about those today. So go ahead and pause the video and try to catch up with this table and write it down in your notes. Okay, now that we've discussed parent geometries and how those result, let's talk about shape possibilities. So if we have two regions of electron density, by the way, this is around the central atom. I ought to have said that. Around central atom, the number of electron regions, there are a few possibilities we're going to see over here, but for this line right here, for two electron regions, there's really just one shape. Imagine your central atom bonded to two other atoms. Okay, and these little lines represent electron regions, electron pairs that repel each other. So just like these balloons are going to spread out and make a linear arrangement, these electron pairs, these bonding pairs, spread out and we get a linear molecule. Okay, there aren't any linear molecules that I know of with three atoms that are going to be rather simple to talk about. So I'm going to actually give you an exception to the octet rule, and I'll draw it out in just a moment. But there's a exception to the octet rule called boron difluoride. Boron difluoride, and I'm sorry, beryllium difluoride, not boron. Beryllium sometimes doesn't follow the octet rule. And so I'm going to draw this structure in a minute, and we'll see how it becomes a linear molecule because of VSEPR. Okay, if we've got three electron regions around the central atom, there's actually two different things that could happen. We could get a trigonal planar molecule, like the parent geometry. Okay. So those three bonding pairs repel each other and they spread out and give a trigonal planar molecule. Or if one of these is a lone pair of electrons. I'm going to put a lone pair of electrons up top. That lone pair is going to repel bonding pairs because it's just electrons repelling other electrons. We call this configuration bent. So let me give you an example of each one of these. For trigonal planar, an example for that is another exception to the octet rule, boron trifluoride. That must have been the one I was thinking of a little bit ago. And sulfur dioxide. Sulfur dioxide is going to have a bent arrangement, and we'll see that in just a moment. Now, what if you have 4 electron regions around your central atom, like these 4 balloons? There are 3 possible shapes that we can get. The first shape is simply the name of the parent geometry, tetrahedral. So those are a little bit hard to draw. But we've got 2 of these white atoms in the plane of the board, one that's coming out towards us away from the central atom, and then one back behind the plane of the board. That's a tetrahedral molecule, and there's lots of molecules that are tetrahedral like that. Another possibility is if you replace one of these bonds with a lone pair. So I'm going to put the lone pair on top here, and then draw everything else the same. We've got an atom here coming towards us, and then an atom going away from us, back behind the board. This is a particular shape called trigonal pyramidal. It makes a little pyramid with a triangle on its base. So trigonal pyramidal. Trigonal pyramidal shape. That can happen under the parent geometry of tetrahedral shape. There is a third possible shape, and it's a different type of bent when we have 2 lone pairs repelling each other along with 2 bonding pairs, and I'm going to draw the bonds coming towards us and away from us. There. This is called a bent molecule. And actually the water molecule falls into that category. I'm going to try to clean up that atom that's in the back of the molecule. Still getting the hang of this tablet, drawing with it and everything like that. So there's 3 possible shape geometries that can result from the parent geometry. An example of a tetrahedral molecule is the methane molecule, CH4. Ammonia is an example of a trigonal pyramidal molecule, and water is an example of a bent molecule that's bent with tetrahedral parent geometry. Okay, so I've given you these examples, but I want to actually show you how this works out using VSEPR. To use VSEPR, we have to start with a valid Lewis structure. Okay, and so let me see if I can't scoot over a little bit more. I might just have to jump to another page, but I'm going to use these same examples and show you how VSEPR works, and we'll see how these shapes result. Okay, so our first example was that exception to the octet rule, beryllium difluoride. Now, since it's an exception to the octet rule, I wouldn't ask you to draw the Lewis structure, but I'm going to go ahead and draw the Lewis structure for you. Fluorines don't ever violate the octet rule. So notice both of these fluorine atoms have an octet, but the beryllium atom here in the middle only has 4 valence electrons. It's violating the octet rule. And so I wouldn't ask you to draw the Lewis structure, but now that we have the Lewis structure, you might be wondering what's the shape of the real molecule. VSEPR will allow us to predict the shape of the real molecule. Okay, because this is a real substance. And, another valid way to draw this Lewis structure, somebody else might draw it this way. See, when I draw it this way, it looks like it's bent. And when I draw it the other way, it looks straight. And so the question is, what's the real molecule look like? So to use VSEPR, we recognize that valence shell electron pairs repel, like these balloons repel. So what we want to do here is count up the number of valence electron pairs around the central atom. So identify your central atom, the one that's in the middle of your structure. Okay, so beryllium's in the middle. And then what we want to do is count up the number of electron pairs around the central atom. Okay, so no matter how we've drawn it, you see that we have 2 electron pairs around the central atom. Okay? So according to VSEPR, there's only one thing that can happen. It will be a linear molecule. It must be a linear molecule because these electron pairs, they repel. And when they repel, they get as far away from each other as they can. So if they happen to be kind of close, we can imagine that there's some repulsion between those two. The negative charges repel, and they get as far away from each other as they can. And so what results is this linear shape. So beryllium difluoride is a linear molecule because 2 electron pairs repel to the max. They get as far away from each other as they can, and that happens to be a bond angle of 180 degrees, so it's linear. Okay, if you're in geometry right now, you'll know that the bond angle of a line is 180 degrees. Okay, and so that's as far away as those could get from each other. Just like these balloons push against one another, and they naturally adopted that linear shape. Let's try it for these other molecules over here. Beryllium trifluoride, sulfur dioxide. Let's see what happens with them. Okay, so boron trifluoride. We've got, this is another exception to the octet rule, so I'll have to draw you the Lewis structure. Trifluoride. The fluorines all have an octet, but the beryllium is violating the octet rule. Okay, and so what we want to do is locate the central atom, which is of course the boron atom, and now count up the number of electron pairs around the central atom. And we see that there are 3 electron pairs. Okay, and these are all bonds. They're all bonding pairs. Okay, they all have atoms attached to them. And so what's going to happen is those 3 electron pairs repel in the same way that these 3 balloons push against one another. And we're going to get a trigonal planar molecule. Beryllium trifluoride's trigonal planar. Bond angles of 120 degrees all the way around. So here we can see that maybe these atoms are a little bit too close to one another, right? And there's a lot of room over here on this side of the molecule. So these are going to spread out, and we're going to get something that would be better drawn, perhaps, this way, if we wanted to indicate the actual shape of the molecule. Okay. The fluorine atoms are separated by bond angles of 120 degrees. Okay. Now the other one is sulfur dioxide. We're going to see that that's got a bent shape. So sulfur dioxide, let me just jump into it. This is one whose Lewis structure you should be able to draw, right? 6 electrons from sulfur, and then 2 times 6 from oxygen. There's 18 valence electrons in this structure. And this is a molecule that actually has 2 resonance structures. We could have the double bond on the left-hand side, or we could have the double bond on the right-hand side. Both of those are valid Lewis structures. Now this molecule, the way I've drawn it, it looks linear. But if we want to know the shape of the real molecule, we need to use VSEPR. We can actually pick either one of sulfur dioxide's resonance structures. So we could use this one on the left or the one on the right to figure out the shape of the real molecule. So what we want to do is locate our central atom again, which is the sulfur, and now we're going to count up the number of electron pairs around the central atom. So the lone pair is of course a pair, the bond over here is a pair, and it turns out this double bond, technically that's 4 electrons, 2 pairs, but as a double bond we're going to treat it like a single region of electron density. And we call that an effective pair. There are 3 effective pairs of electrons around the central atom. Okay. So the double bond counts as 1 electron pair, 1 effective pair. So the lone pair, this bond over here, and this double bond, that's 3 effective pairs. Okay, and so by the way, if we use this other resonance structure, we determine the same thing, right? 3 effective pairs, and notice we've got a lone pair. So we go back up here and we can see that when we have 3 regions of electrons and one of them is a lone pair, that's a bent configuration. Okay, so let's draw this molecule the way it would actually be in reality, a little bit more realistic. Have the lone pair on top, and then the bonds would be kind of repelled downward because all of those electrons around the sulfur repel each other. Okay, so this double bond is repelling that lone pair, and that lone pair is repelling the single bond, and the single bond's repelling the double bond. Okay, and so we end up with a bent configuration. Now, what's the difference between trigonal planar and bent? It's the lone pair. The shape of the molecule is determined by where the atoms are. Here we have 3 bonded atoms. These white atoms are bonded. And down here it's just 2 bonded atoms with a lone pair on top. So if you're just focusing on where the atoms are, okay, right? If you're just looking at where the atoms are, and I've tried to highlight that in pink here, this is a trigonal planar thing, and this is just bent. The lone pair doesn't really have an atom up there. That's just electrons. Okay, so we have a bent molecule in the case of sulfur dioxide. All right, so that's the basic idea. And so I'd like for you actually to continue on to the other video where we're going to work through these other shapes, but we'll see how this applies. And it's all about counting up the number of electron regions. Those are called effective pairs of electrons. Count up the effective pairs of electrons around your central atom, and that allows you to determine the shapes of the molecules.